Hi, my name is Shahina Anak Perempuan Doraisami, and I will be doing a presentation on the topic Organic Chemistry in the Forensic World. This is for the subject Organic Chemistry. My ID is 0120250200278. The main focus of this presentation will be the role of organic compounds, enhancement of latent fingerprints, and lastly, anti-counterfeiting technologies. As for the introduction, forensic science is the application of science principles and methods to support legal decision making in matters of criminal and civil law. A big part of forensic science is including the collection of evidences such as genetic materials, trace chemicals, fingerprints, and other physical evidences. The key areas of forensic science. Firstly, there is DNA coding, which identifies suspects based on genetic material. Next, there is toxicology, which detects drugs and poisons in biological samples. Third, we have ballistics, which is used to examine firearm evidence and material. And then there is also serology, which studies blood and bodily fluids. Now we will be talking about the types of fingerprint analysis. First, we have patent fingerprints, which means visible prints. It is left by substances like blood, ink, or paint. It can also be photographed. Next, we have plastic fingerprints. It is left by materials like wax, soap, or clay. It can also be photographed as patent fingerprints. And lastly, we have latent fingerprints, which means invisible prints made by sweat, oils, and needs specific techniques to identify it. For latent fingerprint identification, there are three methods mentioned. First one is physical method, which is powder dusting, where colored powders are used to adhere sweat residues, and vacuum metal deposition, where visibility is improved by thin metal layers. Next is chemical methods. Ninhedrin reaction means where fingerprint will be reacting with the amino acids in sweat, turning it purple. Next is cyanoacrylate superglue fuming, where white polymerized images are produced, and iodine fuming, where fingerprints become temporarily brown. And lastly, nanotechnology based methods, including quantum dots, which provide high resolution imaging by emitting fluorescent light, and gold nanoparticles, which increase fingerprint image contrast. There are three regions for fingerprint. Firstly, there are visible regions, which provide direct color change upon reaction. For example, ninhedrin, as mentioned before, turns fingerprints purple. All red O turns fingerprints red, and solvent black 3. Secondly, there is luminescent regions, which emit fluorescent signals under UV light, for example, Nile red and Nile blue. And lastly, there are dual regions, which show both visible and luminescent properties. For example, Genipin produces blue fluorescence and visible print. Recent breakthroughs include fluorescent imidazole derivatives, which detect sweat pores, benzazole dyes that enhance blood stain detection, tetraphenylethyne-based dyes, which have cost-effective alternatives, and B and tetraphene derivatives used for enhanced luminescent fingerprint imaging. There are also certain challenges faced in this field. For example, fingerprint residue changing over time. Volatile substances and water evaporate rapidly, and over time, lipids and amino acids break down yet stay longer. Next, technical limitations. Certain regions perform poorly on non porous surfaces like glass and plastic, but well on porous surfaces, for example, paper, cloth. In some situations, fingerprint regions may become less effective or fade. And lastly, the need for innovation. More fingerprint regions that are non toxic, sensitive, and stable are needed. Researchers are creating affordable, environmental friendly materials. Moving on to anti counterfeiting applications. This is widely spread in fake banknotes, passports, certificates, and medicines that pose a risk in society. Technologies used in anti counterfeiting are photofluorochromic compounds, which emit different colors under specific lights. And then there is dianthryl sulfoxide dyes, which provide multicolor emission for authentication. And lastly, there is spiropyrin based materials that show reversible luminescence for security printing. Elaborated research in fingerprint analysis includes recent innovations in forensic science like covalent organic polymers COPs, which include fluorescent probes for level 3 fingerprint details. Next is azomethine zinc 2 complexes, which are excellent adherents for fine grained fingerprint analysis. Next, we have conjugated polyelectrolytes, which enable fingerprint detection without interference. Advantages of new materials include higher sensitivity and reliability, affordable and non toxic substitutes, and improved functionality across more surfaces. The challenges with traditional methods include toxicity of some fingerprint powders, expensive regions which limit widespread in forensic use. To improve the situation, we need safer, cost effective solutions like BN tetraphane derivatives, cost effective luminescent materials, 1,4 disubstitute triazoles, which have non toxic powders for safer investigations. And future goals in forensic science field include eco-friendly regions for law enforcement, AI assisted forensic analysis for faster identification because the widespread of AI is being known to more people. As a conclusion, all things considered, the paper makes a significant addition to forensic science by providing perceptive developments in fingerprint identification and security uses. It establishes the groundwork for safer, more inventive, and efficient forensic procedures by bridging the gap between organic chemistry and forensic technology. Future research should, however, focus on accessibility and practical applications to make sure that these developments help forensic and law enforcement experts everywhere. That is all for my presentation. Thank you for watching.